Okay, so now we continue with a single phase full wave uncontrolled rectifier. So again, the course outcome or the session outcome will be that after completing this session, the student shall be able to, first one will be describe the operation of the rectifier, derive the quantities related to the performance of the rectifier, which means you're able to derive the output voltage, the average of the output voltage, and we look into the harmonics, and that will be the course outcome number 2. Course outcome number 3 or session outcome number 3 will be solve problems related to the rectifier, and finally you also will be able to simulate the circuits using PSIM. Okay, so let's go to the monograph again. All right, so here it's under 4.3, which is single phase full wave uncontrolled rectifier. The first load that we're going to analyze is using the resistive load, a purely resistive load. So to construct or to make it as a full wave uncontrolled rectifier, we're going to add another 3 identical diodes. So for half wave, you only utilize 1 diode. But for the single phase full wave uncontrolled rectifier, we're going to add another 3 diodes, namely, and they are labeled as such. We have D1, D2, and this is known as the diagonal pair of diodes, and we have another pair which is D3 and D4. And then, so it is connected to the R here. So the anode of the diode 1 will be connected to the supply voltage, as well as diode 3 will be connected to the negative polarity of the supply. But for D2, the cathode will be connected to the negative, and then D4, the cathode will be connected to the positive of the supply voltage. Right, so let's have a look of what happens to the circuit and try to get the output voltage waveform of the output voltage and describe the operations, and finally we're going to derive and so on and so forth. Okay, so let's have a look. Again, when you want to explain the circuit operation, always refer to or make the supply voltage as the reference to describe of your operations of the circuits. Okay, so again, this is positive half cycle, this is a negative half cycle of the supply voltage. So here in the waveform here, you have the voltage, output voltage waveforms, which is labeled as the blue waveform here. The red waveform is the supply voltage, and the bottom here is the output current as well as the input current. Okay, so the output current will copy the input current, output voltage, because it's a purely resistive load. So current I equals to V divided by R. Okay, let's have a look at the circuit operation. Okay, so during positive half cycle of the supply voltage, we're going to see that D1 and D2 will be more positive, and they are forward bias. So D1 and D2 will be forward, will experience a forward bias, and the current also tends to start to flow in that direction. Okay, so therefore D1 and D2 will be on, and D3 and D4, however, the other diagonal diodes will be off, because it's experiencing reverse bias, and the current also opposed to the level of the diodes here. So D1, D2 will be operating during positive half cycles. So we have D1 and D2 operate during positive half cycles, and therefore the diode will appear as a short circuit. When it's on, it will appear as a short circuit. So this is on, short circuit, and D3 will be off, isn't it? D3 and D4 will be off, and therefore if you look at this point, the VDC, which is a voltage across your load here. Okay, so this is your VDC. So the output voltage will be equals to the supply voltage, and that's why if you look at this waveform, the output voltage copy the supply voltage during positive half cycle. And let's proceed with the negative half cycle. What happens during the negative half cycle? So during the negative half cycle, so now the supply voltage becomes more negative, and therefore D1 and D2 will experience a negative or reverse bias, and D3 and D4 will experience a positive uh, bias. It's a forward bias, okay? Forward bias, and current now also start to flow in that direction. Okay, so now current will start to flow in that directions. Okay, so again, when this happens, the diode 3 and diode 2 will be short circuit, and D1 D2 will be open circuit. And now the polarity of the supply voltage, the polarity of the output voltage now will be the opposite to the supply voltage, because this will always be positive and negative of VDC, and now it will actually oppose the supply voltage waveform. And that's why during negative half cycles, okay, during negative half cycle, the output voltage actually the mirror image or the opposite waveform of the supply voltage, and therefore now you're going to have the output voltage will be having this pulse. Okay, so it will be halfway full wave rectifier output voltage. So that will be the output voltage, and the pulse, okay, the waveform actually repeats by pi radian or 180 degrees. So it repeats by pi degree instead of 2 pi, so you repeat by pi degree here. Okay, so this is pi, this is 2 pi. Okay, so it repeat by pi, not the 2 pi as what we did for the single phase half wave rectifier before. Right? Okay, so the output voltage, the output current now actually copy the voltage waveform, and it is scaled down by a factor of R, right? Because I equals to V divided by R. So it's a purely resistive load. It will follow exactly as the waveform of the output voltage waveform, but it's going to be scaled down by R. So the output voltage or the output current will actually equals to that wave shape, the blue waveforms here. So this is your output current. Right. So when you have that output current, and we know that the input current is flowing in that direction, isn't it? Okay, so the input current always we assume that and always flow in that directions. Okay, so during positive half cycle, it will carry the same output current, isn't it? Okay, so this is output current, and input current will be equals to the output current. So that's why if you look at the input current, the red waveform, it will follow exactly as the output voltage here waveforms. But during negative half cycles, so this is your current flowing here, and now the current becomes negative, isn't it? So if you follow that direction, this is the direction of the input current during negative half cycles, and that's why the input current during negative half cycles will actually the opposite to your IDC here, opposite to the IDC. So the current at the input also sinusoidal. Okay, so the input current also sinusoidal, follows the same as the supply voltage. So that is will be the the single phase full wave uncontrolled rectifier. So that will be the output voltage waveforms and the currents as well as the input currents. And now we're going to derive for the output voltage. Right, so the detailed expression, don't worry, the detailed expression is the monograph, so you just read again, try to understand. Okay, so for the average output voltage, you have to derive. Okay, look at this. This is a general equation. Always memorize these general equation. The average is always the integration for the whole cycles depending on the waveform. So you integrate for one cycles of the waveform, and you have to divide by t, the period. So if you look at the waveform again, the output voltage waveform, again, I've mentioned to you that the waveform repeat by pi radian, isn't it? So you repeat by pi. So the t here now actually convert into pi. It's no longer 2 pi. So the period here is equals to pi, and then you integrate from 0 to pi. The waveform is the sinusoidal waveform with the peak of v peak sine theta, and then if you integrate that, solve that, you're going to get dv2 multiplied by v peak over pi. So this is the average output voltage waveform, and the current can be obtained by using this equation, 2 v peak over pi r. Right? So simulate the above PSIM and compare. So I leave it to you how to simulate that, or can I just quickly move into the PSIM? Sorry for that. So now let's have a look. So this is a PSIM. So please, I hope you can draw it yourself. So you have supply voltage here 339, or you can put it as a 240 multiplied by square root 2 if you like. You can have 240 multiplied by square root 2, sorry, forgot 2, with a 50 hertz frequency. And then you have this D1, D2, D3, D4, and then don't forget the supply, the probe. The VDC now has to be the point-to-point voltage probe. And you cannot measure from this point. You cannot have this single node probe to measure your output voltage. So if you use the single node voltage probe, you will measure from that point. You measure from that point to the ground, okay, which is wrong. You have to use the node to node, this two terminals probe like this. So you measure exactly from this point to that point to measure the output voltage. Okay, and again, the simulation parameters, you have to refresh back what I did share with you during the class. What is a time step? So the time step is actually used by the PSIM to calculate the value of your circuits. For example, the voltage, the current, right? So you start with the time step of the minimum, which is 0.000. You can have this. This is 1 to the to the power 1 to the power 10 to the power of -5. Okay, and the total time is the running time, how long you're going to run your simulations, and just ignore the print time. Sorry, the print time is when you want to have a start to your simulation data to be safe. Okay, let's say you want to simulate for 2 cycles. One cycle is 20 milliseconds. So here I'm going to simulate for 2 cycles, 0.02 and 0.04. So 2 cycles. So if you want to tell PSIM to save the data starting at 0.02, which is after 1 cycle, then you want to start to save the data, then you put it as a 0.02. So you have to play around with this, because for demo version, the maximum number of points that it can be saved is only 6,000 points, right? So the longer if you have a longer print time, you will get more data to be saved, right? Once you have that data which is exceed the 6,000 points for demo, it will stop your simulation, so you will get the correct output waveform, and you cannot do the measurement and the waveform will be wrong. Okay, will not be correct. So you have to set properly. So in this case, you have, if you have 2 cycles only, and then you have a time step of 1 to the power of 10 minus 5, then it should be okay, right? Or else you need to adjust this. These three elements here is very important. Okay, so I'm going to leave it as it is, 0.04 with the time step of 1 to the power of 10 minus 5, and then print time of 0. So I'm going to run this. Okay, so now I have this the results now. So I'm going to put in VS VDC. Let's have a look. Okay, there you are. Okay, so you can control the size of your, you can adjust the setting of your waveforms. You double click. Okay, so you have select curve here, curve, screen. So you can adjust that by using curve. If you want to make it bold, you can have 2, and then VDC with 3, for example. Then you get a clearer waveform. So this is a VS VDC, and if you want to measure, then you use this button over here. Okay, so there's a few measurements that you can do here. The first one is the average value. The next one is the RMS, and this is the absolute of the average, what is of that. And you can also have the power factor, but to be able to calculate for the power factor, you must have voltage and current waveform together in the waveform. The same waveform, the same screen, you must have voltage and current, then you'll be able to calculate for power factor. And also you have this average power calculation, the apparent power, as well as the THD of your current or voltage, right? So you can compare your theoretical calculation, we have that before. Okay, use that calculation, and then you can compare with your PSIM. Okay, so for example, in here I'm going to get the average of the supply voltage as well, VDC. So if I click that, I'm going to see the VDC is 216.13 volt, and VS, which is very small. Of course, if you take the average of the supply voltage, it is always 0, isn't it? Because it's sinusoidal. Okay, so that is how you're going to use the PSIM, and please make sure that you start to use now. From time to time, I'm going to have we're going to deal with the PSIM. Okay, right? So again, problem. Okay, so now we're going to continue with the resistive and inductive load. So we have a single phase full wave rectifier, and the load now become resistive and inductive load, which is normally the practical. In practical, we do have this R+L. Okay, so if you look at the waveform, the blue waveform here actually shows the output voltage waveform, and the rest is the voltage across your L. The green waveform here, and the red waveform is actually the voltage across the R. VR. Okay, so if you look carefully, the output voltage is similar, is same as what we have before with a resistive load. It is a full wave with the waveforms that copy the supply voltage for positive half cycle, and then it will be the opposite or the mirror image of the supply voltage for the negative half cycles. Okay, but if you look at this green waveform, which is the voltage across the inductor, it becomes 0 whenever VDC equals to VR. For example, at this point where VDC equals to VR. So if you have this, if you take the KVL across this loop, okay, if you take KVL across this loop, then you're going to have VDC equals to VR plus VL, isn't it? Okay, so the voltage across L equals to VDC minus VR. So whenever VDC equals to VR, and we have the voltage across inductor become 0, and you have a positive voltage across inductor, and then you have a negative voltage. So this is where the current start to charge and discharge. So when this happens, if you look at the output current now, it become continuous. Continuous, which means the current doesn't fall to 0. Yeah? It is continuous current. This is termed as a continuous output current. And the ripple, which is the value between peak to peak of the output current here, depends on the size of inductor here. Okay, as you increase the L, the ripple will become smaller. Okay, all right, so now let's look at the input current. So again, input current actually carries the output current. So if you look at this waveform at the beginning, because the circuits still undergo the transient periods, transients period, you're going to see it will start at 0, and then it increased, and then we have a negative current from the IDC here, and then for the next cycles, if you observe, it is no longer 0 here, isn't it? I mean, it start with some value here. Okay, if you look closely, it start with some value compared to from 0 at this point, isn't it? So so when you do the simulation, you have to be careful with this. If you want to do measurement, if you want to measure, for example, the average of the output current here, this is you have to remove the first part of the cycle. For example, here you must make sure that you don't want to display this in the circuit, the waveforms, and then you can do the measurement. Okay, so you have to let this simulation time be longer, leave it a bit longer. For example, you want to have 5 cycles, and then you start to record for the last 2 cycles. So you have 5 cycles running, but you only record and display at the waveform for the last 2 cycles, so that you get into it steady state value. For example, you have this steady state waveform here. Okay, so this is steady state, whereby you see that the cycles, the waveform is symmetrical between one cycle to another cycles. Okay, so you better be careful with this. All right, so the thing is, if you look at the waveform, as we increase, look at the nodes here for the output voltage similar expansion as the previous section. Since the load now consists of inductor, the load current become continuous. The average output voltage is similar to equation before, 4.42. If you look at 4.42, this is the equation. Right? And as the load becoming highly inductive load, for example, for if you drive a motor, right? If you have a motor at the output, so the current will be usually a highly inductive load, and the current will be ripple-free current. So you can model, you can replace. Replace is whereby you remove. Right? To model it in the simulation, you remove the R+L, and then you put in the ripple-free current, which is the constant current at the output. Okay, that's what we did in the notes here. So you're going to replace that R1 plus L. So you remove that and you replace with a constant current. So if you do that for a highly inductive load conditions, you're going to see that the output current become continuous. This is actually the waveform with the 100 millihenries. Yeah? Just now we have 10 millihenries. This is the waveform with the 10 henries. The ripple is very big, large compared to the 100 millihenry. So if you change to 100 millihenry, then you see a smaller ripple. And if you look at the input current now, the input current becomes a square waveform, isn't it? So if you replace with a constant current, and for simplicity, to simplify our analysis after this, we're going to replace the R plus L with the constant current IDC. So if you do that, then you're going to have a nice input, a nice square waveform at the input side. Okay, have a nice square waveforms at the input side, and uh, the the amplitude will be from IDC and minus IDC, whatever the current that you set here. Okay, so therefore this is exactly as the same what we did in the second chapter, chapter number 2, when we describe on the harmonics of a square waveform. So this is similar to that. So you can follow again the explanation, the derivation on chapter 2. And finally, you're going to find out that the input current can be represented by this equation, 4 IDC over n pi. This is Cn. Remember, this is Cn. Okay, and then you have sine n omega t, because phi n is 0. Alright, because your phi n is 0, so therefore you don't have the phi n inside your n omega t plus 0 here. Okay? So this is your equation, and n is always for odd. For a square waveform, n is always for odd, 1, 3, 5, 7. So the first individual sinusoidal waveform will be at 4 IDC over pi sine omega t, and then we have 4 IDC over 3 pi sine 3 omega t, and the rest 3, 5th, 7th, 3rd, 5th, and 7th harmonics, and this is your fundamental component, right? So, and if you want to refer to the harmonic spectrum, you're going to refer back to figure 2.8. So this is the harmonic spectrum of a square waveform. Okay, so please have a look, and therefore you have 4 IDC on problem. So you can problem 1 in single phase. So we have a problem 1 here. So please make sure that you calculate and simulate and get all these values here. The result are the answers for this equation, these questions, and look also the total harmonic distortion and input power factor. So I think yes, I provide here the solution for number 1, which is the total harmonic distortion. So you use the equation before, the THD equals to square root IS over IS1 squared minus 1 multiplied by 100%, and IS1, so IS1 is the fundamental component, the RMS of the fundamental component. Remember, you have fundamental and the rest is the harmonics. So you get the value of IS1 here. This is with the head, isn't it? So it's a peak value. So if you want to get the RS1, which is the RMS, you just simply divide by square root 2, as what we did here. So this is IS1. So 4 IDC over square root 2 pi. Okay, and then if you refer back to the equation 2.5, you can get the RMS of the square waveform, which is equals to IDC. Okay, so therefore, if you put into the equation, then you find out that the THD equals to 48.4%. And do the same for the power factor. So power factor always what? Go back to that. So power factor is always the RMS of the fundamental divided by the IS multiplied by cos P1. So here phi is 0, so you have cos 0, which is 1. You need to find IS1 and IS, and that will give you the result is 0.9, and you will get that 0.9. So prove it that you have a power factor of a square waveform with a sinusoidal voltage equals to 0.9. Okay, so now let's move on to the resistive, inductive, and back EMF again. So you have back EMF because again we have this again motor, and then the R plus L. So here is very large inductor here, and then you have this back EMF. So this is your IDC. Again, if you look at the output voltage, it is still the similar rectified voltage waveform. Okay, so the output voltage will be a similar voltage waveform, and IAC also is a square waveform, and so it resembles the square waveform. So the harmonic spectrum will be similar to figure 2.8. Okay, all right, I think that's all. Thank you.